All right, guys. So we got the released 2024 AP Chemistry Free Response. So I went through the test and made a little answer key, and I just want to go through it. So obviously, you can just scroll through the key if that's what you would prefer to do. But if you want a little bit more of an explanation, um, watch the video. So overall, thought pretty straightforward. There were a couple questions. Maybe there was a curveball or two in there, but nothing too major. And I thought if you used logic, you could probably figure it out. So other than that, I thought you were pretty prepared. Hopefully you felt prepared. Um, and let's just see. Hopefully you think you got, you know, hopefully you remember what you put down, and hopefully it kind of agrees with, you know, and if not, well, now we know. So let's dive into it. All right, so remember the first few questions are worth 10 points. So the first thing I kind of do is I like to go through and see how many prompts there are, meaning like question one, like how many different parts are there. And there's 9 prompts, so that means one of the prompts is worth 2 points. Now, there's no way for us to know which one is worth 2 points. I have an idea of what I think the one is worth 2 points, but and I'll tell you when I get there. But for the most part, they're all worth 1 point, and one of them is going to be worth 2 points. Okay. So first question, pretty easy. Which one of these hydrogens is the acidic hydrogen? It's the one that's on the OH, but also has the double bond O connected to the same carbon, right? That's the organic acid functional group, and so it's that hydrogen that's the acidic hydrogen. All right, so hopefully you circled that one, and not that one. That one's just on the alcohol group. You need the hydrogen on the acid group. Okay. And I'm not going to sit here and read the questions, so you can read the questions. You can pause the video, or you can get your own copy of it and follow along. Okay, so for part B, we just need to calculate the molarity of the solution we're preparing. So we need to do moles divided by liters. So we would take our grams of sodium hydroxide. They were friendly enough to give us the molar mass. And so we'll do 10.22 divided by 44 or 40. That'll give us moles, and then divided by the volume, but it has to be in liters. So divided by 0.5 liters, that'll give us our molarity. So you could have capital M here, or moles per liter, but you need 3 sig digs because the volume had 3 sig digs. You're good plus or minus 1. So if you just said 0.51, or if you had 0.511, whatever the next digit was, that would be fine as well. Okay. All right, next page, we got a titration curve here. The first question they ask us is, based on the titration curve, calculate or approximate the pKa. So remember, pH equals pKa at the half equivalence point. So the equivalence point is 16 milliliters, so the half equivalence point would be 8. If we go up to here 8, it's close to 4, but it's just under 4, so that's why I said 3.9. So pKa is around 3.9, okay? This X is here to answer the next question. So they give us a representation of of what's going on in the flask at a point in time during the titration. And what we need to notice here is we have a lot more of the acid than we do the conjugate base. So I'm calling this HA, and I'm calling this A minus. So we have 2 times HA than A minus. So remember, at the half equivalence point, we have equal amounts. So if this were the half equivalence point, we would have the same amount of HA as we do A minus. But we have double the HA. So we haven't neutralized as much of the HA. So that means we're before the half equivalence point, and we're kind of at the half equivalence point. So we're kind of at the quarter equivalence point. So we would go to around 4 milliliters. And that's where, that's the point of the titration where which this diagram is representing, okay? So I wouldn't use HA and A minus. You probably could, because they use that notation on the formula sheet. But really, it's just the amount of this is 2 times the amount of that, and that's why we're here. If it was the other way around, we would be at around 12, and if they were equal amounts, we would be at the half equivalence point. If all we had was sodium and A minus, and that was it, that would be at the equivalence point. That would be here, okay? All right, so moving forward, now they do the same titration. So the same amount of acid is titrated, but we doubled the base concentration. So it's only going to take half the volume to reach the equivalence point. So you have to draw a titration curve here where the equivalence point is at 8 milliliters instead of 16 milliliters added. And you would really want the end of the titration to be at a higher pH because the hydroxide is more concentrated. So you would end up with a more basic solution at the end of the titration than this one. So as this is curving off this way, it would be higher than up here. I'm not sure what they would be looking for, but the main part would be that the equivalence point would be at 8 milliliters versus 16 milliliters, essentially. Okay. All right, so the acid base kind of goes into a thermo question. So they give us all the information of trying to figure out the delta H of the reaction. And we used 100 milliliters of each solution. And we used the same volume, the same molarity, and they react in a 1-to-1 ratio because the acid was monoprotic. And the hydroxide's coming in with one hydroxide here. So it's a 1-to-1 ratio, so there really is no limiting reactant, or they're each the limiting reactant, I guess. If the reaction goes to completion, all of the lactic acid is going to be gone, all of the hydroxide is going to be gone. But understand, when we mix them together, the combined volume would be 200 milliliters. And they give us the density of the solution, but it's 1 gram per milliliter. So our solution is going to end up being 200 grams. And they tell us the heat capacity is 4.2, so essentially the same heat capacity of water. And they give us the initial temperature, and they give us the final temperature, right? So the first part 1 here, all we're doing is Q equals MCAT. But we'd have to know to plug in 200 grams because we have a 200 milliliter solution and the density is 1 gram per milliliter. We'd find our delta T, and we get our joules, okay? You don't need the negative because it's just asking for the quantity of heat produced. You're going to need to know that when you calculate the delta H at the end, it's going to be negative because the temperature went up, meaning the reaction is exothermic. So negative delta H, energy is released as the reaction proceeds. But for this one, you just need this value here, 2 significant digits because of the heat capacity. When we do our delta T, we end up with just 2 significant digits. So yeah, 2 sig digs here. I think if you put a negative sign, you'd be okay, but you don't need it, and it's just asking for the quantity, okay? For this one, now, I think this is the one that's probably worth 2 points, probably 2 points to know to make it a negative delta H, 1 point to know to make it negative, and then 1 point to know that you have to, first convert it to kilojoules and then divide by moles to get kilojoules per mole. So the first thing to do is flip the sign, make it negative because it was an exothermic reaction. The second thing to do was to convert your joules to kilojoules, but then that was kilojoules per, this much of reactant reacting. So what we have to do is divide by the moles. So if we do the liters times the molarity, that gives us moles. So that's where I got the 0.05. So 0.05 moles of lactic acid reacted or 0.05 moles of sodium hydroxide reacted, either way. And we would divide by moles of that. And because the coefficients of those would be 1 in the equation, per mole of lactic acid or per mole of sodium hydroxide would also be per mole of the reaction. So it comes out to be around negative 54 kilojoules per mole of reaction. It would definitely have to be a negative sign here. Okay, if you put positive, you would maybe that would be 1 point, maybe 1 point for 54, and then 1 point for knowing to make it negative. So maybe if you got 54 but just didn't have the negative sign there, you might get 1 point for this. I'm not sure. No, I don't know if this is the 2.1. I'm just thinking there's a lot going on in this part of the question, and so I could see where this is where they would award you 2 points if you got it right. And the next one is a agree or disagree question, and it's asking. It's saying the student claims if heat was lost to the calorimeter and the surrounding air during the reaction, then the experimental value for the heat of reaction would be smaller in magnitude than the actual value. And they ask, do you agree or disagree? And you would agree. the heat loss to the air would mean the delta T would not, the measured delta T in lab would not be as high as it should be. And if you have a lower value for delta T, you would end up with a lower value for heat, and that would give you a lower value for change in heat calculated. Okay. All right, let's move on to question 2. All right, question 2 had 10 prompts. So if you go through question 2, there's 10 different parts to it, and so that means you know each one is 1 point each. So if it's a question where you have to justify or explain or show your work doing a calculation, it's going to be only 1 point, and you have to have both things correct. Okay. All right, so this one's just say, hey, here's how many moles of CO2 are produced, and so how many grams. So that's just moles to grams. Hopefully you didn't have to waste time calculating the molar mass of CO2. I hope 44.01 is stapled in your mind for the rest of your life. I hope you have nightmares where you're waking up going 44.01, and because it's forever stuck in your mind. 18.02, 44.01, right? 32, all the 28.02, all that good stuff. 1.01, 2.02. Okay. So just moles times the molar mass, all right? Moles was 3 sig digs, so 3 sig digs here. All right, then it gives us the pressure, the volume, the pressure and the temperature of the gas. We know the moles of the gas from the previous part, and it's just asking for the volume. So here comes Pivnert to the rescue. You can't use 22.4 liters per mole. So if you took this and multiplied by 22.4, that would be incorrect because you're not at STP. So you got to use Pivnert. So we're solving for V. Use the correct R value. If you're going to use 8 atmospheres, make sure you convert your temperature to Kelvin. And we're solving for V. And whenever you solve for V using the ideal gas law, it's going to be liters unless you adjust your R value. So 0.219 liters. Okay. All right, the next one is more like kinetics question. So if you crush it up, if you crush up something that you're dissolving in water, what are you doing? You're increasing its surface area. And if you increase its surface area, it's going to react faster because you have more places for collisions to occur. So number 1 would just be increases. Notice it didn't say justify, so increases, that's all you would need. And then step 2, it would take less time to dissolve when it's crushed up because the increased surface area increases the overall number of collision sites, which will cause the reaction to occur faster. Okay. All right. Good thing we had just talked kinetics, so that was fresh in your mind. Part 3, when the reaction is complete, will the volume of CO2, so this is in the next trial where they crushed up the solid instead of having chunks. They grinded up the solid. Would the amount of CO2 produced be greater than, less than, or equal to? So just because the reaction is happening faster doesn't mean you're going to get more product. If the reaction goes to completion and you use the same amount of reactant, you'll end up with the same amount of product, right? So it should be equal there. All right, part C. So I don't know, maybe you guys had this experience too. When I sat down to take this test, when I got to this question, I knew the answer was the sodium bicarbonate was the limiting reactant. Because when you look at the 2 trials, this mass stayed the same, this mass increased, and the moles of CO2 increased. So obviously, this was the limiting one. But I was struggling to figure out how I was going to put that in words. And so rather than sitting there and going like, how am I going to word this correctly? Because I knew what the answer was, but I was having trouble communicating it. So I just decided to go with a calculation. So doing this, I had to figure out the molar masses of the whatever, was this the lactic acid and the sodium? No, whatever that acid was. I'm thinking about a different reaction. Malic acid, sorry. So I had to calculate the molar mass of malic acid and the molar mass of sodium bicarbonate real quickly. But that's pretty easy, especially like you probably have, you know what hydrogen is, 1.01, you know what carbon is, 12.01, you know that oxygen is 16. Maybe you don't know sodium's 22.99, but you probably do. So you could probably easily, quickly calculate those molar masses. So in trial 3, if we take the amount of malic acid and divide by its molar mass times its mole ratio, and again, you'd have to go back up to this equation. It's a 2-to-1 ratio. If all of the malic acid reacts, you can get this many moles of CO2. And if we do the same thing with the given amount of sodium bicarbonate, we would get this amount of CO2. That's the smaller amount, and that's the amount that we actually got. So this was the limiting reactant. So I just did a calculation to justify, which is perfectly fine. I'm sure some of you more eloquent people were able to come up with the words to reason it out. I just was struggling, so I was just like, I'm just going to do a calculation. So let's go to part D. The reaction has a value of delta S greater than 0, so a positive delta S. That means entropy is increasing. Now, there's a lot of justification to this. The main part I went with was with the particles, the solid particles becoming aqueous particles. Solid particles can't move, but aqueous particles can. So because the particles can now move in the aqueous state, that means it's more random or more disordered or more complexity to the system. So that was my justification. But again, you're describing this entire reaction. So if you go back to this page, we're going from two aqueous things to a gaseous thing, okay? So because we have two aqueous things to a gaseous thing, gases are way more disordered. So that's probably the better explanation. I think this is probably not the best, because I was just talking about for this to dissolve. So if starting with this, but if they're talking about the entropy change of this reaction, it's already assuming this had already dissolved. So you'd really probably have to go with the fact that you're producing gas versus just things that are in the aqueous state, and gaseous particles are much more entropic or much more random or much more disordered than an aqueous system. So that's why there's an increase in randomness or disorder. That's probably the better explanation now that I'm thinking about it. Okay. All right. If we go to part E, the student claims that the reaction is thermodynamically favorable at all temperatures because delta S is positive and the reaction is endothermic. So remember, endothermic means positive delta H. Do you agree or disagree? So we would disagree here, because the only time a reaction is always favored no matter what is when you have a negative delta H, when it's exothermic with a positive delta S. So if this had said exothermic, then yeah, I agree. But since it was endothermic, a positive delta H combined with a positive delta S, remember that's favorable at higher temperatures, not favorable at all temperatures. You'd have to have a negative delta H and a positive delta S to always be favorable. Okay. All right, so part F, they give us the step-by-step protonation of the acid, or ionization of the acid. So shows the first H plus dissociating, the second H plus dissociating. So the Ka1 for the first H plus and the Ka2 for the second H plus. And they just say calculate pKa2. So remember, P means take the negative log. So pKa2, you just take the negative log of Ka2. So just take the negative log of this number, and that's how you get pKa2. Okay. And then a buffer system was made between this and this. So this buffer system, this conjugate base with this weak acid, and the pH is 7. And so we would just use the Henderson-Hasselbalch, and we solve for that ratio. X would be that ratio in the Henderson-Hasselbalch. We just figured out the pKa, 6.07, so that would go here. pH of 7 would go here, and we would just solve for X. Okay, so notice it didn't ask us to solve for one of these values, it just solved for the ratio. So when I solve for X, it comes out to be around 8.5. Okay. All right, we move on to question 3. So here, question 3 there were only 8 prompts, so that means 2 of the prompts are worth 2 points. I'm guessing maybe the first one is because you have to have 2 oxidation states, so maybe 1 point for that one and 1 point for that one, but maybe not. I don't know. It's just it's a guessing game, but at least so 2 of these questions are going to be worth 2 points. Okay. So here, part A, we got silver, solid silver is in its elemental state, so its oxidation state is 0 in this ionic compound. Silver's +1. If you didn't remember that silver's always a +1 ion, you'd have to know that sulfide is 2-, so each silver would have to be +1. If you put +2 here, that's wrong. Remember, you don't indicate the total, you indicate what each individual silver is, so +1 there. Okay. They're asking why would an alloy with silver and copper be substitutional, not interstitial? And it's because you have very similar atomic radii, so it would have to be substitutional. The copper is not small enough to fit in between the spaces that the silver spheres would make, so it can't be interstitial. Okay. This one is saying, using principles of atomic structure and Coulomb's law, explain why silver has a larger radius than copper. And so remember, when you're bringing up structure, you want to talk about energy levels, sublevels, all that good stuff. But when they bring in Coulomb's law, that means you kind of have to bring in the nucleus into account, because that's the positive charge that the electrons are attracted to. And you might want to bring in shielding into this, because copper has less protons, but the reason why the electrons are more attracted to the nucleus is because it has less shielding. All right. So copper has 4 energy levels of electrons. Silver has 5 energy levels of electrons. Even though silver has a higher nuclear charge, its electrons experience more shielding due to the larger number of core electrons. You probably need to go a little bit more in detail here, but you just say copper, because there's less shielding, or because there's less electrons between the valence shell and the nucleus of copper, there'd be a stronger Coulombic attraction with its nucleus, that kind of thing. But that's essentially the type of explanation they're looking for. Okay. If we go to part C, I initially just calculated the moles of silver sulfide because I ran through it fast. And then when I went back to double check, I went, oh, wait, they just wanted silver. So you'd have to subtract to get the mass of the silver sulfide. They gave you the molar mass, so divide by the molar mass of silver sulfide to get moles of silver sulfide, and then recognize there's 2 moles of silver for 1 mole of silver sulfide to get moles of silver. Okay. All right. So here, part D is where I thought it was a little tricky, but when you get to this part of part D, it helps you make your mistake, fix your mistake if you're kind of on top of it. So here, they give us 2 half reactions, right? And if I'm not reading the question carefully, I might go, okay, well, if I want to get a spontaneous or thermodynamically favored redox reaction out of these 2 half reactions, then this is the one I have to reverse. That'll become a negative, but when I add them, I'll end up with an overall positive cell potential, okay? And that's what I was thinking when I first did this one. So I had, in part I had the reverse reaction than the one I have here on the answer key, okay? But when you read the question, you are producing solid RH, okay? So this reaction has to happen as is. So this is the reaction that has to be reversed, okay? And notice you're producing solid RH from RH2SO43, so from a solution that has RH3 plus ions. So this reaction is happening as is. This is the one that needs to be reversed. Okay, so to get the net ionic equation, first you're going to reverse this, so the water is going to be on this side and all this stuff is going to be on that side. And remember, you have to get the electrons to cancel. So you have to multiply this reaction by 4 and this reaction by 3 so that you end up with 12 electrons in this equation and 12 electrons in that equation. So this would be the overall net ionic equation. And the overall potential for this reaction would be the oxidation potential plus the reduction potential. The reduction potential in this case is 0.8, and the oxidation potential would be negative 1.23. I hope you didn't make this mistake. It should be pretty fresh, but hopefully when you multiply by 3 and multiply by 4, you didn't touch these values. Okay. The only thing you had to do with this one is because we reversed that reaction, you had to flip the sign. Okay. So that comes out to be a negative 0.43 volts. But understand, I made the mistake. I had this reverse reaction here, and I had it correctly balanced, but I had the reverse reaction, and I had positive 0.43 volts here. But then when I got to this part of the question, it said, based on your answer in part D2, explain why the process requires an external power source. I was like, it requires an external power source, meaning it's not thermodynamically favored, meaning it has a negative potential. Then I went back and I read the question more carefully, and I was like, oh, you idiot. You just wasted so much time. So you had to reverse this reaction. This was a negative, and that's why, because a negative potential means the reaction is not thermodynamically favored. In order to make a non-spontaneous or non-thermodynamically favored oxidation reduction potential go, you have to apply an external power or voltage source. Okay. And then part E was just electrostoic. So again, unit 6 fresh in our heads. So hopefully we got this one. We would take our grams of Ru, divide by its molar mass. We'd have to look it up on the periodic table. The mole ratio is 3 to 1. 3 moles of electrons for every 1 mole of RH plated, right? 3 moles for every 1 mole of solid RH, okay? And then we'd have to use Faraday's constant to convert moles of electrons to coulombs, and then we divide by the amps, divide by the current to convert from coulombs to seconds. And it comes out to be around 3,900 seconds. Okay. All right, so this one might be worth 2 points because of all the stoichiometry. I don't know what the other one that might be worth 2 points would be. Yeah, I don't know. I don't know what the other 2-pointer is, but yeah. Okay, so I'm going to chop this up into 2 parts.